Hello. Hello, everyone. Welcome to our webinar today. We'll just wait 1 or 2 more minutes for additional participants to arrive. And then we will start with our presentations. So welcome to everybody who has joined in the meantime to our webinar on membrane reactors, one step forward towards industrial implementation. So then let's get going. So hello, welcome everybody to our webinar today on membrane reactors, one step forward towards industrial implementation, which is presented to you by the MACBETH project. We will tell you more about that in a minute. But now let's first look at the organization of today's webinar. As you might have noticed, all attendees are on mute, but you can ask questions via the question function of the webinar menu. Perhaps we can take a second to test that. So if you have found the question function in your menu, please take a second and say hello. Hello, Omar. Great. Great. Hello, Thomas. Irene. Great. I see you have found the function. So that's wonderful. So via this function, you will be able to ask questions during the webinar, and we will answer these during the question and answer section at the end of the webinar. So that's wonderful. And additional information is that the slides and also a recording of this webinar will be available from our website after the webinar next week. So you will be able to revisit this webinar if you are interested. So then let's take a quick look at our agenda for today. We will first have a short introduction to the MACBETH project by Frank Stenger of Evonik and Dr. Fausto Gallucci of the TU Eindhoven. We will then hear about membrane reactors for hydroformylation by Vinzenz Fleischer of Evonik. Subsequently, we will hear about membrane reactors for hydrogen production presented by Fausto Gallucci of TU Eindhoven. Then we will continue to membrane reactors for propane dehydrogenation presented by Vittoria Cosentino of KT. To subsequently move on to membrane reactors for biocatalytical oil cleavage presented by David Liese of Enzymicals. And then last but not least, we have a roundtable and question and answers, which will be moderated by Frank Stenger of Evonik and Fausto Gallucci of TU Eindhoven. So then let's get going. I will now give the floor to Fausto to start with our first presentation with an introduction of the MACBETH project.
Okay, can you see my screen now?
Yes.
Yes. Okay, welcome everyone. I can give the floor to Frank because he will start with the introduction.
Yeah, thanks, Fausto. Welcome from my side as well. My name is Frank Stenger from Evonik. I act as the technical coordinator of the MACBETH project, and together with Fausto, we'll give you first a short overview of the MACBETH project. Next slide, please, Fausto. So first of all, we will start with the acknowledgement, which you usually do at the end, but not to forget about that. And worth to mention, it's a European funded project under Horizon 2020. Gets budget of around 21 million euros throughout the project time of 5 months. So it's really a long-term project. As you see later on, it aims on a rather high technology readiness level. And the consortium consists out of 24 partners really throughout Europe. So we really can say it's a big project, and yes, with really some great goals that we see on the next slide. MACBETH is the acronym for Membranes and Catalysis Beyond Economic and Technological Hurdles, really aiming at a breakthrough technology by combining catalytic synthesis steps with the separation units afterwards in a single catalytic newly created reactor. Really some revolutionary things that we try to implement, and not in a development state, but on a demonstration level. So the task really is to demonstrate that this technology will work at a readiness level of 7. So it means in industrial near an environment, we'll see later on in the demonstration cases. And not just this, we want to mature the technology developed and transfer it to other industries, even within that project. So a little bit aside from the typical chemical applications that we aim at, we want to apply that to the biotechnology sector that you will see later on, even within that project. And to really to roll out the ideas, the knowledge and the know-how to other applications after the project, and really to keep the knowledge inside. It's also the idea to create a spin-off of that European funded project that we call a lighthouse, where all the knowledge is stored within the catalytic membrane reactors. If we go to the next slide, you will see we don't start right from the scratch, from the beginning. There's a lot of pre-work already done in predecessor projects. Four of them you can see here. There's the Romeo project on one side, where large-scale chemical processes were looked at, water gas shift reaction and hydroformylation. Out of that project, we take the hydroformylation as a very promising use case that you will see later on, and to demonstrate the membrane reactor technology in a 2-in-1 reactor. Bionico was the second European funded project aiming on the hydrogen production and separation in a membrane reactor itself, focusing on the biogas production. So this demonstration case will be elaborated within MACBETH as well, and on top of that, even a second showcase for the hydrogen case. From the Carina project, there were promising results in the conversion of high alkanes and CO2 into higher value chemicals that we will look at for the propane dehydrogenation case. And finally, there's the Cosmos project, a predecessor project aiming on the biocatalytical oil cleavage, where the bases were laid in terms of highly selective enzyme technologies. And the task is really to combine these base findings for the biocatalytical oil cleavages and bring it now into the thinking of the membrane reactor technology. So really a great basis that we could start off. With having this basis, the basis was set for the whole project setup that Fausto would introduce to you in the following.
Thank you very much, Frank. I'm Fausto Gallucci from Eindhoven University. And as you saw, we have quite a big project, and we want to demonstrate at TRL 7 4 technologies. And Frank already mentioned that for the hydrogen production, we have a second demonstrator. So in total, we have 5 demonstrations at TRL 7. And how we put and set up the project together is realizing that the different teams have a single point in common, which is the integration of reaction and separation in membrane reactors. And to do that, you have building blocks, which are the supports for catalysts and membranes, the membranes themselves, and the catalyst to be integrated. So what we do is we start from what we achieved in the different project at TRL 5, what we call building blocks. We scale up the building blocks, we integrate in membrane reactors, and finally we do the demonstration. And as we also said before, one of the output of this project will be also the creation of lighthouse membrane reactors, where we collectively put together all the knowledge and we offer the knowledge to other partners that want to test membrane reactors, so membranes and reactors for their application. So in this way, we thought that we can accelerate the exploitation of the membrane reactors for other type of reactions. Now, the project is quite big. It's 24 partners in 10 countries. And I'm also happy to say that soon will be 25 and next year will be 26 partners. So as an experience in European project, I'm very happy that this is the project where partners start to join the project rather than leaving the project. And we have from Germany, Italy, Spain. We have from the Netherlands, Belgium, and France, UK, and Turkey as well. So you see that this is quite diverse. And we have 6 prototypes, and here you see where the prototypes will be tested for TRL 7. We have 4 cases. One is the hydrogen, the hydroformylation, propane dehydrogenation, and the BOC case. And today you will see a presentation, a short presentation of all the cases, 15 minutes per presentation, and then afterwards we have time for discussion. And the agenda of today will be basically after this short introduction, we will start with the hydroformylation, and then I will continue with the hydrogen production, and then we go on. And at the end, we have 20 minutes for hopefully your questions. Before I leave back the words for the hydroformylation, I want to remind that we have a project website, but also the LinkedIn and Twitter channels where we also share most of the results, and some of the results that we show today are already shared in these links. Thank you very much, and I would like to give back the words for the hydroformylation case.
Thank you. So I hope you can see my screen now.
Yes.
Yes.
Perfect. So let me just enable the laser pointer. So I'm Vinzenz Fleischer from Evonik, and today I would give you a brief overview about the HIFO case at the MACBETH project. So agenda is I will give a short introduction about what is the hydroformylation reaction in detail and what is the status now, and what are we doing with the hydroformylation in the MACBETH project. This is, as introduced before, a challenging task to go really a big step forward to create a new reactor design. So we will see many changes, and we had a great team to support this development. And finally, I would give you a status of today and an outlook what we are going on. So let's start with the hydroformylation reaction. What's this? In our case, we are converting 1,N-2-butenes with CO and hydrogen into C5 aldehydes, namely the Valère aldehyde. And this is classically done by a rhodium ligand system. And under hydroformylation conditions, you have also side reactions, so namely the hydration of your aldehyde to the alcohol, the condensation of your products, or even the hydration of your ligand, of your reactant. And as an example of how is this system applied in chemical industry, you see an example on the right-hand side. So typically this is a homogeneous catalyst process, meaning you're storing the catalyst in a liquid phase, heavily boiling solvent, and then you are bubbling your reactants through this reactor. And all your reactants have to be dissolved in the liquid phase. Now they are converted in the liquid phase to the aldehyde, and then the aldehyde is driven by thermodynamics again into gas phase, and your reactor will outlet and contains a mixed gas which has to pass a complex downstream system to achieve finally the pentanal as your target product. If you would like to go and learn more about the hydroformylation and all its details, there are also scientific books, so I recommend this one. And on the next slide, I show you what we have done so far with the hydroformylation to convert it to MACBETH. What we are doing now is we are changing the system from a homogeneous into a heterogeneous one. And to do so, we are using such monolith structures to support the catalyst material. And what we're doing additionally, we are wrapping a membrane on the outer wall of the monolith system. We are doing the same chemistry, so we are inserting olefin, hydrogen, and CO into it. We are still converting it to pentanal, but now there's an interplay between the reactor and the membrane. The membrane works as a separation unit, but it affects the reactor, the reaction, and the whole process in a tremendous way, with a highlight in the focus of sustainability, because it clearly simplifies your process. So because of your putting two things into one process unit, you have the advantage that you can put out your product just in time, preventing several reactions like the formation of byproducts. And with this, you increase your selectivity of the process on the one hand, and on the other hand, in a typical fixed bed reactor, your pentanal will act as a diluent in the bottom part. But by removing it as soon as possible, you can intensify the whole process with this. And if you apply this technology, you're clearly saving carbon dioxide emissions. And because you integrate a big part of your downstream in one unit, you increase also the energy efficiency. So now you have a nice sketch about how it works, but how is it realized? And this is sketched here. So here is our monolith, and this monolith is a porous ceramic made of silicon carbide. So it's a really tough material. And this material is completely porous with an open pore network, so that all your reactants can be transported into every channel all the time. And this channel, you can see here, the pore structure includes another material, an SiO2 layer, which is stored in those pores. But the pores are still open, so that you have again completely transport to the whole system. And finally, at the outside of this monolith, we have a supported skin material, which is there to keep the membrane, which is a polymer, in place. Because of such large pores, if you just would add a polymer simply at this ceramic, your membrane will not stick as long as required. And the skin is just a small layer of additional silicon carbide materials, which provide another pore texture. And for this reason, your membrane keeps in position. So now I've shown how is the monolith constructed, but where's the catalyst? How do you do that? And for industry application, it requires obviously a very simple system to do so, to be applicable. And this is sketched here. So to introduce the catalyst to the reactor, we have a so-called coating procedure. So it requires a solvent, which can you easily evaporate. And in this solvent, you put in your classical materials. So the rhodium precursor, the ligand, and the stabilizer. And what you can do in parallel is just mount the monolith to the setup, and then you can introduce your coating solution to the reactor, filling everything. So this means the monolith inside and the pores. And this happens at ambient pressure and at room temperature. So it's not very highly sophisticated anymore. It's applicable even in a larger scale. And just after waiting a half an hour, then you can just release your coating solution, and then your monolith is ready to perform. You just have to evaporate your solvent, and you have to increase the temperature, and then the system is ready to operate, so that you can just go further to increase pressure, temperature, and you feed now your reaction feed into the system, and the monolith works. And to get at this status, obviously requires a great team with several experts to improve, to optimize, and even to develop it. And this is an overview. So LICTech and CSIC take care for the monolith, for the wash coat, and for the skin. Hirion provides the membrane and all the experiments how to put this membrane to the wall in a way that we can mount it on big setups. The DTU takes care for the whole coating process and coating optimization strategies. The FAU takes care to test the system because we have a complex interplay, even if it looks very simple. And we as Evonik, we are doing upscaling experiments, long time experiments, and we are also highly interested to model this whole system because the interplays are still complex, but they work. So what is the status for today? Today, we are right here on the left-hand side of this picture. So we are using still lab setups in a scale where we can operate the system for more than 1,000 hours and beyond. And our next step will be to go into such a field to construct the pilot plan, which will have a clearly bigger dimension than we will have here in this lab chapel. And with this, I would like to thank you. And even if you have questions after the webinar, please get in contact with our team. So here is a slide who contributes from each company and university to the HIFO case. Thanks for your attention. And with this slide, I would like to hand over.
Thank you. I'll hand over to Fausto for the presentation on hydrogen production.
Hello again. Can you see my screen again?
Yes, perfect.
Thank you. So I'm Fausto Gallucci again, and now I will show you the status of membrane reactors for hydrogen production. Before that, I want to, let me see if it's working. I want to show a little bit what we do in our group in Eindhoven University. Our research is in integration of reaction and separation and reaction and energy management. Generally, we work with integration of reaction and membrane separation or chemical looping sorption kind of separation. And we work also with plasma, and MACBETH is basically based on membrane, integration of membrane and reaction. Now, for the hydrogen, what we mentioned before is that we started from the results of Bionico. And here you see the reason why we use a membrane reactor. If you start from biogas or from natural gas, you know that you can produce hydrogen going through a number of steps which are all equilibrium, all produce hydrogen, but they work at different temperature. So the reforming is high temperature, and then you have lower temperature water gas shift, and finally the purification. On the other hand, if you integrate the separation of hydrogen in the reactor, you can basically combine all the steps in a single one, which helps you to decrease the capex, but you can also decrease the temperature because you shift the equilibrium, and this helps you to increase the efficiency. Now, in MACBETH, we started from Bionico, where we design a reactor for biogas conversion, and we want to demonstrate two prototypes for two different technologies. One is the autothermal reforming of biogas, the other one is steam reforming of natural gas. The reason why we want to do two is that they share many common themes, the catalysts, the membranes, but the architecture is a little bit different. In one case, it's more compact but less efficient. In the other case, it's a little bit more involved because you have recycles, but it's also more efficient. We work with palladium membranes because in this way you have much higher selectivity and you can get pure hydrogen in one step without cleaning afterwards. And of course, we also try to improve the modeling and all the knowledge on membrane reactor to move to a spin-off company that will be part of MACBETH. Now, as I mentioned before, we have for the different lines, we have something in common, that is the catalyst, the membrane, the support, and the reactors. What does it mean for hydrogen? For hydrogen, for the catalyst is to optimize the amount of catalyst compared to the amount of hydrogen that we want to produce, because in the past, till Bionico, we played quite safe. We just put enough catalyst to be always at the equilibrium. But now that we are closer to commercialization, we have to really optimize the catalyst, and especially because in the last 2 years, the cost of different materials, including the active material for our catalyst, is increased quite a lot. So we have to optimize that. For the membranes, what we are working on especially is on metallic supported membranes. This includes also the support, of course. The reason is that if you have metallic supported membranes, the sealing is much cheaper, the selectivity is much higher. On the other hand, the cost of the actual support is too high, so we are working on trying to reduce the cost. And of course, the reactor is testing the prototypes at TRL 7. So I will show a few results of all of these points. The first is the catalyst. So what we did in Bionico, or till Bionico, I should say, is developing a fluidized bed catalyst. Why we use a fluidized bed is because the membranes are very selective, high flux. So to avoid any mass and heat transfer limitation, we work with a fluidized bed. But as I said, in Bionico, we just had so much catalyst that there was no problem in conversion. Now what we want to do is to really reduce the amount of catalyst to the one that we want. And I want to show you a few modeling and experimental results. The blue points are the experimental results done by Johnson Matthey that is producing our catalyst. And you see that in principle, we can have very good results with our model if we use the right model for the right catalyst. And in case we use nickel catalyst, which has a much lower productivity, as you see here, and we put enough nickel catalyst and enough rhodium catalyst, basically there is no difference. The reactor will produce the amount of hydrogen and will be just limited by the hydrogen that you remove from the reactor itself. But if we reduce the amount of catalyst, you see that with the rhodium, we can go to 10% or even lower than 10% and still be able to produce the amount of hydrogen that we want to produce. While with nickel, then at a certain point, we start to be limited by kinetics. Since we are working with rhodium, makes sense to go very low in the amount of catalyst that you need for the hydrogen production. Then we use this model also to map the operation of the reactor as a function of temperature, as a function of amount of hydrogen produced, and as you see also as amount of catalyst. And for our catalyst, as soon as we reach around 10%, then there is basically no difference in the performance of the reactor at any temperature. Now, for the metallic support, as I said before, we are able to produce metallic supported membranes. There are different people able to produce the metallic supported membranes. But if you want to do a large-scale membrane reactor, then the cost of the support are too high, especially because there are only a few companies that, or as a matter of fact, only one company that produces the support with the quality such that we can do the membrane. So what we do in MACBETH, we start from relatively cheap support, actually our filters. You cannot simply put the palladium on top of it. What we do, we modify the support, the surface of the support. Then we put a coating of ceramic to avoid any interdiffusion movement of metal, and finally we put the palladium on top of it. So I want to show a few tests that we did in the lab. You see that basically you can modify and polish the surface. As a function of time, your surface gets more and more polished, more and more smooth, as you see here. This is the original support, 3 hours, 6 hours, 9 hours. You get more and more smooth surface. On the other hand, you are also covering some of the pores. So, and the permeation through the support decreases. So we found out that there is a trade-off, and this trade-off is around 4 to 6 hours. You can have the good quality to produce the membranes. And here you see a few membranes that we produced. This is a first plating and then a replating, and you have relatively good membranes. You see that we are able to do either 4 to 10 micron membranes. You can see also here the interdiffusion barrier. Where we are now is that we know how to modify the support, but the layer is not as good as we need for the reactor. And you see here that, of course, there is a little bit of leakage still, and this leakage is because of the polished support has still some big pores, and we are now optimizing how to cover these big pores. So at the moment, the ideal selectivity is below 1,000, and for the project, we should go at above 20,000. The next step, as I told you, is the demonstration. We have two demonstrations. I show here only a picture of one. We went through the design, modeling design, HAZOP, and you see here a scheme during the HAZOP. And here you see the real prototype. So for the hydrogen, we are a little bit ahead compared to the other lines. Prototypes already being assembled. You see a lot of parts here, and here another picture of the prototype. And just to show you how it looks like, this is a 20 cubic meter prototype. It's still quite empty because it's still a research prototype, but is smaller than a container. And this now is being transported for the final connection and the FAT, and then we will be able to test this reactor, hopefully next year. For the other prototype, we did exactly the same, modeling, optimization, HAZOP, and here is a picture of a new hall where the prototype will be installed. I have a picture of the container, not the picture of what is inside the container, but you can imagine, again, a prototype where is within a container. Compared to the reforming, the steam reforming that I showed before, the autothermal reforming is smaller. So it goes in a standard container, while the other one was not in a standard container. And to finish with, what we are doing now is to further optimize the amount of catalyst, scale up the membrane production till we can produce all the membranes, hopefully next year for the prototype. Finalize the two prototypes. One is almost finalized. The other one is a little bit behind, but we are confident that also the second one by next year will be finished. And then the main challenge we saw at the moment is that the supply of components is not as straightforward, because those components are too large for a lab scale and are too small for a larger scale. So we are in between, and it's very complicated to get the right components. But still, we are confident that both prototypes will be finished well in time for the demonstration. And with this, thank you very much, and I will hand over the word again.
Thank you, Fausto. I will now hand over to Vittoria for the presentation on propane dehydrogenation.
Okay, can you see my screen?
Yes.
Yes, okay. So, good afternoon to all. Pointer. Okay, so I'm Vittoria Cosentino from KT, and today I will illustrate the PDH line for MACBETH project. So in this presentation we will see some information about propylene with a focus on thermodynamic and kinetics aspects. We will then talk about the background of the PDH membrane-based technology, and to analyze what led us to the definition of the MACBETH objectives and the new innovative PDH line, and to conclude a brief focus on the status of the activities. So while we are talking about propylene, the propylene today is market is very varied, as propylene is the basis of many commonly used products, mostly plastics and adhesives. In the graph you can see a breakdown of the market, where the majority of the production is towards polypropylene. Currently, propylene is produced as a byproduct of ethylene, so in process as steam cracking and fluid catalytic cracking. But today, on-purpose technologies are becoming more popular, since the demand of propylene is widely increasing, while the demand of ethylene is decreasing. So the main purpose technologies are olefin conversion, methanol to propylene or olefin, and propane dehydrogenation. And in this latest we have as commercial technologies CATOFIN. There is something, okay. CATOFIN, Oleflex, STAR, FBD, and PDH. All of these technologies, as said before, are based on the propane dehydrogenation. In blue you can see the reaction, and as you can see, this reaction is strongly endothermic, so is favored at high temperature, and occurs with an increasing in moles, so is also favored at low pressure. And so industrially the operating conditions are temperature between 560 and 650 degrees C, and pressure up to 5 bar. The reaction system is very complex, so these are the main side reaction which occur in parallel with the hydrogenation, and propylene is not the most favorite product. So we need a catalyst to favor the propane conversion and the propylene selectivity. But however, even with a catalyst, the propane conversion is quite low, and the selectivity of propylene doesn't exceed the 90% in the most optimistic case. So we have lots of byproducts which should be separated, and so the downstream separation unit is very complex. The main problem is, however, the coke formation, and because the coke can deactivate the catalyst sites and also can lead to different problems during the operation of the reactor. And the problem is that as said before, the reaction is endothermic, so it's favored at high temperature, but also coke is favored at high temperature. So this means we need to operate at lower temperature, which further reduce the propane conversion, and above all, we need to regenerate the catalyst during the operation. So indeed, the commercialized technology have a complex system of reaction regeneration schemes. So what would be a solution? A solution could be introduced inside the reactor hydrogen perm-selectivity membranes. In this way, removing the hydrogen allows to shift the chemical equilibriums towards product as thanks to Le Chatelier principle, and in this way we can enhancing the hydrogen yield at lower temperature. We have moreover other advantages that are the use of a low-grade heat rejected by bottom process, reduce the catalyst regeneration step, potentially reduce the conventional plant capacity, and valorization of the side stream. In this first figure here, we have the propane conversion at different membrane recovery factor and what membrane permeance, sorry. And what we can see is that at higher membrane permeance, the propane conversion increase. It's also interesting that if we fix the propane conversion, for example, in this graph, we have a propane conversion fixed at with okay, you can, I don't know why I don't see all the slide, but okay. At fixing the propane conversion, we can see that the operating temperature with the membrane decrease, and this is important since with the decreasing of operating temperature, we have a significant reduction in coke formation. So there are most positive aspects linked together. But it's also important to highlight that today the membranes for this application have still a lacking stability. So here we can have different membrane reactor configuration. For example, in this slide, we reported a simplified scheme for open architecture and hybrid architecture. And the difference is basically that we have in the open architecture a reactor with only the catalyst, a module for the membrane separation, and another reactor. Instead, in the hybrid architecture, after the membrane module, we can have an integrated reactor in which the membranes and the catalysts are all together inside one vessel. In these slides, there are some pictures of the previous PDH membrane-based project. With this is the pilot plant, and then we have pictures of the catalytic reactor and the membrane module. So, starting from these previous results, the aim of the MACBETH project is to bring the PDH line to a TRL7, and the main objectives are to operate the plant at mild operating condition, so below 540 degrees C, in order to reduce the coke formation, and in this way reduce the catalyst deactivation increase the propylene selectivity, and to have a stable operation of the demo unit for more than 4,000 hours. The partnership is made up of industrial and academic partners involved in different activities inside the line. The core system of the line is a fixed bed reactor in which we have membrane in which we have palladium based membranes for the hydrogen separation that are double skin membranes, and a platinum based catalyst. The operating conditions are between 480 and 540 degrees C with a pressure up to 6 bar. The expected propylene selectivity is about 95-99%, and the demo unit will have a capacity of 2 kilograms of propylene. If we look at the overall process, we have now a comparison between the a simplified Oleflex scheme, that is one of the benchmark process, and the MACBETH scheme. What we can see is that the new membrane reactor allows to consistently reduce the reaction phase, and so also to reduce the reactor area. And furthermore, by since we have a high propylene selectivity, we can also simplify the downstream unit. We in fact we don't need a PSA because we recover the hydrogen from the membrane, and moreover we can simplify the separation unit before the splitter propylene propane. In this way, we estimate a reduction in capex of 15%, and a reduction in opex of 16%. Moreover, the mitigation of the operating temperature, so decreasing in coke formation, and so the need to have the coking cycle less frequently, and the reduce of the separation section lead to a decreasing in the greenhouse emission of 20%, while the reduce the fuel consumption, increase the hydrogen productivity, and reduce the duty of the separation unit lead to an increasing of 20% of the resource and energy efficiency of the line. So basically, these are the objectives set for the PDH line, and at timing level, now we are at the month 24 of the project. So the design of the prototype unit is still in progress, and in parallel the optimization of the catalyst and the new membranes is in progress, and in parallel we start the study of an industrial scheme for this new PDH reactor. At the end of the project, what we want is to have concluded the long-term operation, and we are confident that the results will be positive, and to have a techno-economic assessment of the industrial scale system. So for now it's all. Thank you for your attention, and if there are some questions, we will answer at the end of the other presentation. So I leave the floor to Barbara.
Thank you very much, Vittoria. I will now give the floor to David to tell us more about the biocatalytical oil cleavage.
Okay, can you see the presentation?
Yes, perfect.
Okay, thank you, Barbara. So hello, everyone. This is David Liese from Enzymicals, and I will give you a short overview of the fourth case of the MACBETH project. And we will talk about membrane reactors in the field of biotechnology and the goals that we want to achieve in this exciting project. The BOC case, which stands for Biocatalytic oil cleavage, is the most exotic of the four cases because we make things a little bit different compared to the other three cases. First of all, we will show for the very first time that the idea of an integrated catalytic membrane reactor can be transferred to the field of biotechnology, thus exploiting the full potential of the CMR technology. We, from the BOC case, started at the lowest technical readiness level of all the four cases. This means that we have to develop the whole process a lot faster to achieve the ambitious goals of this project. Therefore, we will take advantage of the experience and knowledge of all the other partners within the MACBETH consortium to make progress really fast. So in a way, we are the role model for the foreseen spin-off company Lighthouse. We joined the MACBETH project with the idea of utilizing both enzymes and membranes in a biocatalytic oil cleavage process to enrich valuable omega-3 fatty acids in fish oil. But before I explain the whole process to you in more detail, let me please first introduce you to all the partners who are involved in the BOC case. So first of all, we from Enzymicals, we are the case leaders of the BOC case and mainly responsible for the process development of the catalytic reaction. Here we closely work together with Chiral Vision from the Netherlands, who are our experts for enzyme immobilization. For all the membrane-related tasks, we have the Vito Institute from Belgium in our team, and Microinnova from Austria are our experts for bringing the process from small batch trials to a continuous flow process. Also, the engineering activities and the construction of the lab and pilot plans are done by Microinnova. Then we have Polimi and the University of Brescia from Italy, who are responsible for all the modeling activities in our case. And last but not least, there is Solutex from Spain, which completes our team. Solutex is well known in the omega-3 fatty acid market and can therefore be a potential end user for the technology that we will develop. Also, Solutex is responsible for the sourcing of the fish oil and acts as a consultant in our case. So the motivation of our project is to enrich omega-3 fatty acids in fish oil, namely EPA and DHA, that are both polyunsaturated fatty acids. EPA benefits the cardiovascular system of the human body, while DHA plays a crucial role in the neurological function of the brain. Unfortunately, the human body itself cannot efficiently produce those omega-3 fatty acids. Therefore, it is necessary to obtain adequate amounts through nutrition, for example, eating fish or dietary supplements. By nature, fish oil is already rich of EPA and DHA, but we want to increase its content even further. Therefore, we will take advantage of the selectivity of an enzyme. Enzymes are biocatalysts which bring different affinities towards their respective substrates. In our case, we want the enzyme to selectively cleave off every other fatty acid, except for the fatty acids of interest, EPA and DHA. and those fatty acids shall remain bound on the glycerol backbone. So here I want to show you how our process works in more detail. So fish oil consists of triglycerides with a wide range of different fatty acids. Our target fatty acids, EPA and DHA, belong to the longer chain fatty acids. So we are treating the fish oil with an enzyme which is more selective to shorter and medium chain fatty acids. These shorter fatty acids better fit the catalytic active site of the enzyme. And when we now add just the right amount of ethanol, we end up with a very complex mixture of mainly mono and diglycerides, as well as fatty acid ethyl esters due to transesterification reactions. Due to the selectivity of the enzyme, most of the target fatty acids will remain on the glycerol backbone and will be enriched in the fish oil. So once we let the reaction run to a certain degree of conversion, the mixture is then passed over a membrane. And the task of the membrane is to separate the fatty acid ethyl esters from the EPA and DHA enriched fish oil. So with this process, we want to increase the EPA and DHA content in fish oil from approximately 30% in the starting material to 50% or even higher in the final product. So next, I want to give you a little insight of our development so far. In the beginning of the project, we were screening a lot of different enzymes. And we found enzymes, for example, enzyme A and enzyme C, which had nice selectivity towards the target fatty acids, but poor activity, resulting in very long reaction times. On the other hand, there are enzymes, for example, enzyme B, which are very active, but possess a bad selectivity profile. So we have to find the best sweet spot between selectivity and activity. Now, what do I mean by selectivity? If we have a look at the fatty acid composition of fish oil, there are a lot of different fatty acids with different chain length ranging from C14 to C22, as well as saturated and unsaturated fatty acids. As I already told you, EPA and DHA belong to the polyunsaturated and very long chain fatty acids. So in this slide, I want to emphasize on the individual selectivity of different enzymes towards various fatty acids. Enzyme A, for example, is selective towards medium-chained fatty acids, thus increasing the concentration of EPA and DHA in the fish oil. Enzyme B, although very active with short reaction times, only enriches DHA and shows almost no selectivity towards EPA. And enzyme C, on the other hand, has again a nice selectivity profile, increasing the amount of EPA and DHA while selectively cleaving off saturated fatty acids, such as palmitic and myristic acid. So for easy downstream processing, the enzymes that we are using in our process are immobilized on a solid support. This not only aids better process economics, moreover, catalyst reusability is ensured and also structural stability of the enzyme. There are different methods of enzyme immobilization. Here only the physical adsorption on the surface of the carrier and covalent binding of the enzyme are being mentioned. Currently, we are investigating both these options to find the best solution for our process. Now I will briefly talk about the membrane separation process in our case. So, as I already mentioned, after the enzyme catalyzed reaction, we will end up with a complex mixture of triglycerides, diglycerides, and fatty acid ethyl esters. So the task of the membrane will be the removal of the ethyl esters from the reaction mixture. Under ideal conditions, only the ethyl esters permeate through the membrane while retaining the omega-3 enriched fish oil in the retentate. So on this slide, you can see the experimental setup and some first preliminary results of the membrane screening experiments. So when evaluating the data and therefore the performance of the membrane, you have to pay attention to the rejection profile, which indicates the selectivity of the membrane, as well as the permeates, which is a measure of how much product can be treated in a given time frame. And another parameter that influences the permeates in our case is the temperature, because we deal with highly viscous media like fish oil. So the final goal of our project will be an integrated flow process at pilot scale. At the very beginning of the project, the first screening experiments were carried out in 2 milliliters Eppendorf tubes. We then performed parameter optimization trials in 50 milliliters round bottom flasks, as you can see on the left-hand side. And afterwards, a scale up to 6 liters in batch was successful. So we are now transferring the reaction part of the process to a flow setup in lab scale. For our pilot plant, we foresee demonstration runs at 2 different locations. So the initial operation of the pilot plant will be demonstrated in Germany, and long-term stability tests will be performed in Spain. And in order to conveniently transport the pilot plant from one location to another, it will be built inside a containerized system, as you can see here on the right-hand side. And with this, I want to thank you for your attention from the whole Bockcase team. And now it's back to you, Barbara. Thank you.
Thank you very much. That means that we are now starting our question and answer section. I will give the floor back to Fausto and Frank for that purpose. And I would like to invite our audience to ask questions. We can either, or perhaps everyone who has a question can raise his or her hand electronically, and I would then unmute that participant to ask the question. Is there anyone who would like to ask a question to our presenters?
Not many.
No, there is someone. Ivana, you wanted to ask a question.
Yes,
please go
I
ahead.
want to ask the question to the team that presented the dehydrogenation. Do you have any idea how you will deal with the coking while using the membrane reactors? And where do you see here the biggest limitation in the technology for handling the dehydrogenation?
Okay, if I understood well the question, okay, for the cooking, let's say our idea is to reduce the cycle of the cooking, but of course not to avoid that coke is the deformation of coke. That is not, I think it's not possible. But the idea is to reduce the cycles in order to have more hours of operation, let's say. The other question, can you repeat, please?
Where do you think is the biggest limitation in the development? Do you believe it's a catalyst compatibility membrane, or do you see it more in a technological side?
Okay.
Perhaps I can take this one, Vittoria, since we are working on membrane, and I think most of the challenges are there.
Yeah.
You are right. Is the where the coke formation occurs, and with the membranes, basically you can decrease quite a lot the amount of coke formed, but still you need regeneration, so you cannot go to zero coke formed. And depending on the temperature, in some condition, the carbon is deposited more on the membrane than on the catalyst. So the biggest challenge is to make the membrane and the catalyst work very close to each other. So we have a solution for that, such that the membrane works at a temperature a lot lower than the catalyst, and still have the function of decreasing the amount of hydrogen and decrease the temperature of operation. So it's not a straightforward that you put the catalyst in the membrane just in contact, because then still you have carbon formation. You cannot avoid that. You can decrease, as Vittoria said, you can decrease quite a lot, but the carbon will form more on the membrane.
So how do you plan to bring the catalyst on the membrane?
Basically, we want to have the catalyst far from the membrane. So you
Far from the membrane.
Yes, there is a delta T between the catalyst and the membrane.
Ah, okay. So basically your reaction runs on the catalyst, and then the whole mixture goes through a membrane. And
then to a catalyst, and then to a membrane.
Okay.
The membrane, the catalyst are two different. It's not a membrane with the catalyst on the membrane, no, are two different items, let's say. So we try to put together, but are different. It's not a catalytic membrane.
Yeah. Thank you. Thank you very much. Very nice presentations.
Thank you.
Thank you. Then I have a new question by Peng Yan. He's asking in the question function regarding the hydroformylation in membrane reactor. Does it still need solvent?
So I hope you can hear me. Not really. So it's the question about what solving are we talking? So in a classical one, you need clearly a high boiling solvent to keep the catalyst in position. In the membrane reactor, it's not required anymore, because you need just the solvent to put the catalyst into its position, into the wash coat. But right after the evaporation, there's no solvent anymore. So you just have the rhodium, the precursor, and a stabilizer, which is responsible to keep the catalyst inside of the wash coat. So there's no further solvent anymore inside. I hope this answers your question.
Great, thank you. Then I have a next question Peng Yan is saying thank you. So I think that's okay. I have a next written question by Simon Picot van Reu, which I will read out. And after that, I will give the floor to Hartwig Voss and Omar Zea, who both raised their hands. So let's first continue with the question of Simon. which is, I have a question concerning the PD membranes. Are they resistant with the presence of CO up to 3%?
Yes,
gas?
Yes, I can take this one. The membranes are resistant to CO, yes, also to higher. We tested also much higher. And the operation anyway for the reforming is between 450 and 550, where there is very less absorption of CO. So the CO adsorbs on the same site where the hydrogen wants to absorb, so the permeation is reduced, but there is no problem with the membrane. There is no cock formation on the membrane because of CO, also with high amount of CO. And with the higher the temperature, the lower is this problem of absorption. I hope this answered the question.
And then the question continued, what is the purity of the hydrogen in the permeate if the feed stream contains a gas mixture of CO, CO2, CH4, H2, and HO2? H2O, sorry.
Yeah. Yes. The best membranes that we tested till now have a purity of more than 99.999. Of course, not the membrane that I show you in the presentation. That in that case, the purity will be lower than 99.2, I think, or even lower than 99. Sorry. But with the target of selectivity, we can go to fuel cell grade hydrogen directly in one step.
Thank you. And then the last part of Simon's questions concerns H2 recovery.
H2 recovery, yeah, it depends on the reaction rate. Sorry, the reaction system that we considered. You saw that we show also a graph that is done by Politecnico di Milano using modeling, and you see that you can optimize the system based on the recovery. In any case, to have high efficiency, you need a recovery higher than 50%. In the best case, you have a recovery of around 68%, and then you get probably the higher efficiency, depending also on the pressure that you use. So I would say between 50 and 70% is the region where the membrane reactor makes sense efficiency-wise.
Great, thank you. Simon has written, thank you very much. So he's hopefully happy with our answers. I would then now give the floor to Hartwig Voss, who has also raised his hands and a question, I suppose.
Okay,
Hartwig,
can you hear me?
The floor is yours. Yes.
Yeah, can you hear me? Okay, I have some questions according to the hydroformylation case. The butane feed, is it a gas or is it a fluid?
Everything is in gas phase, so there are no liquids inside.
Okay, then you have in principle a MACBETH reactor with a very short way. What's your conversion to you? And you have only one pass. What's the conversion? The conversion of the butane to the aldehyde in this case?
Well, it really depends on the feed, because we have not only one butene, we have also cis and trans butene. And for one butene, I can say it's almost completely converted. And this is also true for the cis-2 butene. Trans-2 butene is very dependent on the ligand, because it's very hard to deactivate, but I can say it's far more than 20, or even going in higher ranges. But it really depends on the feed and also on the ligand which you are using.
Okay, and what's the function of your Pebax membrane outside of your monolith?
It removes the pantanal, because these paths which I have shown are connected with each other. So there is an open pore structure. so that the channels, so the molecules can change the channels very easily by the pores. And the membrane removes the pentanal as soon as possible, so that you avoid high boiler and other side reactions. So I can say we have nearly no conversion into butene, and also the alcohol formation is not present anymore.
Okay, thanks.
Thank you. Then we will move on to the next participant with a question, which is Omar. Omar, I unmuted you. You can now ask your questions if you want.
Yes, hello. Thank you for the presentations. I had a question regarding hydroformylation. So as far as I know, in the Ruhr chemie process, it's also continually separated, and it's also highly selective. So what advantages does this membrane setup offer when compared to the Ruhr chemie process?
Well, honestly, I can't give an adequate answer to this question, I have to say, because I'm not very familiar to your mentioned process right now. Sorry, but I will check that.
Okay. So the other question is, how often will the membrane need to be regenerated?
So the membrane,
generated. Yeah.
No, it has not to be generated. So what we have to keep in mind is the catalyst, because, well, it's still a ligand and has a specific lifetime, but the lifetime of the membrane is far beyond of the lifetime of your catalyst system. So there's no regeneration required.
But also not the catalyst on the membrane?
No, there's not really a significant amount catalyst on the membrane, because the most of the catalyst is stored in the pores of the monolith, and the membrane has just an insignificant amount of catalyst, and it's a polymer membrane, so there's also no catalyst dissolved in this membrane, so it's just a transport effect.
Yeah, okay. Okay, thank you very much.
Thank you, Vinzenz, for your answer. So that were all the questions and all the raised hands for the moment. Is there anybody else who would like to ask a question? Then please either type it in the question box, or please raise your hand so that I can unmute you. There is a new question asked by Mike. Does the hydroformylation catalyst need to be regenerated?
Well, yes, but currently we are doing this in our lab setup for more than 1,000 hours, and currently we have to estimate that we think that we will generate it once a year. So this is just a rough estimation from our current experimental results. And yeah, to see this really in a sufficient industrial environment, we are building this technical readiness 7 plant.
Great, thank you. There's a new question from Ida. It says, as the treatment plants used to purify effluents, and since 21st century, the world is worried due to the huge load of microplastics trapped, how this is supposed to be solved by a membrane reactor. I guess this would be a wastewater treatment application of a membrane reactor. Is that applicable? Can you filter out microplastics? Is that relevant?
Actually, it's very difficult to answer with the membranes that we are using at the moment. I'm not sure for nanofiltration membranes, but this project is really on membrane reactors. This application that you mentioned is membrane separation. I know that there are people working on it, but I'm not in the position to say how good are the membranes at the moment, because we are not working on that application now.
Thank you. We would, in principle, have another 10 minutes to answer questions. Is there anybody else who would like to ask something?
Maybe I have a question, Barbara, just to inspire a little bit the exchange. Maybe a question to David. And you can give kind of your experience in yes, learning from the other partners in order to adapt, yes, the knowledge from the building blocks to your case. And maybe, yes, just a brief, yes, what is your experience so far? How did that work out? Collaboration, yes, in between the partners and really bringing up the BOC case to the level where you are right now.
Yeah, so right from the start of the project, we were in contact with all the partners in the MACBETH consortium, and we located some points. We call it the cross-fertilization issues, where we can learn from the experience of the other partners. And we opened some topics there concerning membranes and also construction-wise with all the partners in the project. Some of the topics ended up to be a dead end that didn't help us in our progress, but also seeing how the other cases engaging problems and solving them, this was also a huge lesson for us. So it is very beneficial to have such a huge consortium and come together from time to time and speak about the problems that we are having.
Thanks, David.
Maybe
this encourages, yes, some outside people as well to to ask questions and to come up with maybe some new ideas, applications. And I think the whole team would be happy, especially as with the lighthouse, having that in mind.
Exactly.
Also, and really, yes, have some new ideas, question whether this is possible with the know-how already generated. So please feel free to contact us and yes, challenge us with your questions and your ideas.
Thank you, Frank. I think that were very good concluding words for our webinar. So if there aren't any more questions, I would like to thank everybody for participating in this webinar, for presenting the MACBETH project in this webinar. And I hope we'll see you again during future events on our website, because we still have 2 years or more than 2 years to go in the project, and I'm sure there will be many more exciting results we are going to share in the future.
Thank you all.
Thank you. All the best to you.
Bye-bye.
Thank you. Bye.
Thank you. Bye.